Okay, so the first kind of surface integral we just discussed was that to find the surface area of a surface given in as a function of x and y. But well, let's generalize into. I mean, let's have a look at this generalized form of a surface integral, for which we have a surface with an equation g of x, y. The partial derivatives are continuous. The usual. So now have a look at that double integral right here. So now this integral that contains this surface area element has something other than 1. But I wonder what would that represent, because again, the double integral with the element of surface area with the 1 in the integrand, that's just the upper surface area, right? That's what all it is. However, if we have something other than a 1, what would that be? Because again, the double integral dA, that's area, right? The double integral with f of x, y, f of x, y, dA, either volume or mass of the planar region. Planar lamina. Let's call it lamina. Well, what would that represent, this surface integral with a function other than a 1? Well, for the simplest case, let's think of this as the mass of this shell, right? That's what it's going to be. Let's think of it. And again, think that is, if f of x, y, z equals to 1, that just takes us back to the upper surface area. All right, guys, there's a little catch here. What is it? Because yes, we're going to be given this function of x, y, and z, a function of 3 variables. However, we have a double integral, so there's room for only 2 variables, all right? X and y. So we need to kill one of those variables. So what are we going to do? Oh, we will write this z in terms of the function g of x or y that represents the surface. So this f of x, y, z is not going to be the surface. This f of x, y, z will be a density function, for instance. So the density at all these different points, okay? So, and the g of x, y, that'll be the surface that represents the surface, the solid, right? Okay. So, and we need to be careful when we have these z variables. We need to kill those z's and write them in terms of x and y's. Okay. Evaluate the surface integral x minus 2y plus z ds, where s is the plane, z equals to 2, and x squared plus y squared less than 1. So that is all the points inside inside the cylinder of radius 1. Let's plot the region. All right, let's plot the region of, or plot the solid. Okay. That is okay. So that's the cylinder. Another. Okay, so that is our cylinder and the plane z equals to 2. All right, z equals to 2. Again, so the intersection between the cylinder and the plane, what is that going to give us? Isn't that a circle that's going to get projected onto the xy plane so we can figure out the limits of integration? You know the drill, all right? So, circle of radius 1, all right? Wait, yeah, radius 1. Unit circle, all right? Okay, let's set up the integral. So that's the double integral of x minus 2y plus z, okay, plus z. And this will be times ds. Be careful. This is no longer an upper surface area. This is no longer upper surface area. So we're finding the mass of this shell given by that region with density given by x minus 2y plus z. All right? Okay, so That's the same as, well, actually I'm going to replace ds with the radical. Z with respect x squared plus z with respect y squared plus 1 dA. Okay, so the surface S, that'll be equal the integral of x minus 2y plus z, okay, times, oh, this one is going to be pretty easy because, okay, the equation of the surface z. What is the partial of z with respect x? What is the partial of z with respect y? They're all zeros, right? They're all zeros. So this will be times the square root of 0 squared plus 0 squared plus 1 dA. All right. We have a problem. This dA will later become either dy dx or dx dy. Did you see the z in the integrand? We need to get rid of it. We need to get rid of this z right here. Replace z with the equation of the surface z. All right? There will be some cases in which it will not be necessary. You'll see. All right, so over surface S, that's the double integral. That's over the region R. Anyway. That equals, okay, x minus 2y plus 2 times, okay, 0 squared plus 0 squared is that 0 plus 1. Isn't that 1? The square root of 1 is just 1. Do we need to write the 1? Not really. dA. Okay. That reduces to this simple double integral. But we are integrated over a circular region. What do you think we should do? Polar, right? Polar. You don't want, I mean, in this case, no, yeah, you don't want it to polar. You don't want it to rectangular. Send it to polar. How about the radius goes between 0 and 1 and the angle goes between 0 and 2 pi? Why is it the angle going between 0 and 2 pi? Because in this case, there's no additional conditions like, oh, only the power in the first octant or anything else. So 0 to pi. All right. So let's replace x in terms of the r and theta. That is r cosine theta minus 2r sine theta plus 2 r dr d theta. Okay? Let me distribute the r because we will need to integrate this with respect to r, so make sure you have a simpler function. So that is the integral from 0 to 2 pi from 0 to 1. That is r squared cosine minus 2r squared sine plus 2r dr d theta. Okay. Let's integrate with respect r. Integrating r squared, that's r cubed over 3 minus r cubed minus 2r cubed over 3 plus r squared. But don't forget the cosine factors. That is the integral from 0 to 2 pi r cubed over 3 cosine minus 2r cubed over 3 sine plus r squared. Evaluated between 0 and 1. Okay, and again, these limits of integration are just for the r variable. All right? I mean, do you guys agree that if we evaluate the lower limit of 0, everything is going to get zeroed out? All right? That's good to know. That you need to write to show the evaluation. Now, 1 cube, 1 cube, 1 cube, 1 squared. Isn't that just 1? Okay. So, oh, don't forget the d theta here. 0 and 2 pi, so that is 1/3 cosine theta minus 2/3 sine theta plus 1 squared, which is 1 d theta. And I mean, the rest of the problem is a pretty basic calculus 1 integral. How about I just give you the result for this? I mean, you can integrate cosine, that's sine. You can integrate negative sine, that's going to be a positive cosine with all these negatives going on, right? You know what we're talking about. Final answer, 2 pi. All right. Final answer, 2 pi. Oh, okay. The next problem. Pretty cool problem. You'll see why. Because, okay, then in the next problem, guys, this is the first time we will ever evaluate a double integral projecting onto a plane that is not the xy plane. Okay, so throughout the study of double and triple integrals that we have done in this class, regardless of the setting, regardless of whether you have one surface, two surfaces, even 17 surfaces at the same time, what do you do? Put all the equations together to see what is the projection onto the xy plane. Why would we do that? Because we are already used to set up integrals in the world of xy. But some integrals may get harder to even set up, not even evaluate them, even just to set up. That in some cases projecting onto the xy plane. If we stick to the xy plane, we're just not going to be able to evaluate such an integral. So in many cases, the trick is to project onto the xy plane or onto the yz plane, which we haven't done ever in the class. All right, we're going to do this in this exercise. All right. Well, we will evaluate this double integral, this surface integral in two different ways. Number one, by what's that? By projecting onto the xy plane, and then we're gonna rework this integral. All right. So, well, there is good news about this integral. Well, that's because did you see how the integrand doesn't have a z, doesn't have the z variable? So we won't have the need to replace that z in terms of xy, like we did it in the previous example. So this is really good. This is awesome. Okay, so the equation of this plane, finding the x-intercepts. Okay, let me write the equation. X plus 2y plus z equals to 6. Okay, so the x-intercept, isn't that 6? The y-intercept, isn't that 3? And the z-intercept, another 6. How about that? All right, graph the plane. Graph the plane. And okay, let me indicate the projection onto the xy plane. All right. Actually, I'm going to do another Cartesian plane, a 2D plane, a 2D graph, to describe this projection onto the xy plane. Okay, so that's x, that's y, that's z. So that is 3 and 6. All right. And that is the equation with y-intercept. So y equals to plus 3. And then what is the slope? 3 over 6, right? Also negative. It's going down. So that's negative a half. Negative 1/2 x plus 3. So that's the equation. And the limits, again, these are, what was that? 6, 3, 6. So that is 0, 6, and 3. Okay. Let's set up this surface integral now. All right. So, oh wait, hold on, not yet. Partial with respect x, -1. Partial with respect y, -2. Oh my God, this is really. We will love it when we are working with planes because their partials are constant, so we won't have to simplify a crazy radical, right? The double integral of x, y, ds, no longer dA, it's ds. To turn this into a dA, okay, what do? That's the integral of the double integral over the region R of x, y, square root of z with respect x squared plus z with respect y squared plus 1 dA. Okay, again. Do you see how we're going from ds to dA? And we added that extra factor of that radical. What do you think that big radical is? it's the Jacobian to go from an element of surface area, from the world of surface area to the world of plane area, right? That's. You see how everything now is a Jacobian? Jacobian here, Jacobian there. All you're gonna be dreaming about Jacobians and Jacobians and Jacobians, right? Yeah, I mean, even when you're exchanging money currency, that conversion factor, it's a Jacobian, right? You can think of it as a Jacobian. Everything is a Jacobian in this world. All right? Okay, let's set up the double integral. Okay, so that's the double integral from 0 to negative 1/2 x plus 3, and from 0 to 3. Okay, that's xy. Square root of, what's that? Negative 1 squared plus negative 2 plus 1 dy dx. Okay? Yes.
Is it from 0 to 3 or 0 to
0 to 6. You're right. From 0 to 6. Okay? And well, 1 squared is 1, 2 squared is 4, plus 4 plus 6, is that the square root of 6? Yes, it's a square root of 6. Double integral from 0 to 6 and from 0 to negative 1/2 x plus 3, what's that? xy dy dx. And I really don't want to spend the whole lecture evaluating this double integral. The hardest part of a double or a triple integral, it's the setup, right? That's what you want to pay more attention here. The evaluating, come on, I mean, again, you're masters of integration at this point, right? Mm-hmm. Yeah, I love the silence when I say this. Yeah. It's delicious. That silence is delicious. Anyway, well, let me give you the result. That's 27 half. Oh, wait. Square. Oh, yeah, 27 over 2 square root of 6. Okay. Finally, for the first time, we're going to set up a double integral in the world other than the xy projection. You'll see how it's going to work. Okay. All right. Example number 6. Rework example 5, projecting S onto the YZ plane, not anymore onto the XY plane. That is, instead of using, check this out, instead of using Z as in terms of X and Y, we will use X in terms of Y and Z because we will be projecting onto the YZ plane. Alright? Okay, let's go about it. Okay, so the same plane we got from before. So the same plane in space. All right, so that's a 6. So that's 6. That's also 6. And that's 3, right? Okay. All right, we will no longer use, okay, because here's the thing. The reason why we always evaluated double and triple integrals projecting onto the XY plane is because the XY plane helps us better to see the solid as bounded below by the floor and bounded above by the roof, right? But when we project this onto another plane, that is this plane right here, all right, which, oh, careful, I'm going to do another two-dimensional projection. Yes, it's a two-dimensional projection, but it's no longer XY because we're projecting onto the YZ plane. This is Y and this is Z. So what are we doing? We're rotating the solid and only focusing on the YZ plane. All right? What's the equation for that? Okay, number 1, so 6, 3, boom, triangle, y equals 6 over 3, isn't that 2? But negative 2, negative 2x plus 6, the plus 6 is the y-intercept of the line. Different equation from before, right? Different equation than before. And what else? Okay, I think that's it, right?
Shouldn't the variables be different?
Yeah, you're right. It's 2y, right? Equals to z. Yep. And that's a good catch, right? So that's what happens when you change to another projection that you're not used to, like right now. Well, I didn't make the mistake on purpose. It was actually a careless mistake, right? I didn't do it on purpose. But yeah, thanks for catching that. So yes, the variable, the choice of variables, careful, it matters. Okay. All right, now, well, so we're going to work with a function x, right? A function x of y and z. So let's write the equation of the plane, that is x plus 2y plus z equals to 6. I'm going to solve for x to obtain a function, an explicit function of y and z. All right? That is 6 minus 2y minus z. Okay, and let's find the partial derivatives. That is x with respect, well, you know what, I'm going to use Leibniz notation, Jacobian notation. Partial of x with respect to y, partial of x with respect z. Okay, so that is going to be -2 and -1. All right, pretty easy, simple constants this time. Okay, so let's set up the surface integral, but be careful with the what's it called, with the variables. Number one, the same surface integral, the same one, the double integral over the surface S of the function xy, which represents the density of the shell, right? What else? Okay, so that is times the square root. It's no longer dz dx and dz dy both squared. This time is partial x with respect to y squared plus partial x with respect z squared plus 1 dA. Let me call it dA for now. Okay. And again, be careful because we are no longer projecting onto the xy plane. Sorry that I repeat myself on this because it's the first time we change the projection. So what is dA going to be? Well, there's two choices for dA. What do you think they are going to be? Or no longer dy dx or dx dy, right? So dz dy or dy dz. Okay, we'll see which one do we get. All right. Okay, so that is the double integral over the surface S, or over the region, no longer the surface, over the region, because you already wrote the element of surface. xy, that's the square root of -2 squared plus -1 squared plus 1. Let me do dz dy. Because in this setting right here, on the yz plane that we did on to the right of this tetrahedron, which one is the dependent variable? An independent variable, right? So let's follow this order: dependent and then independent, right? That's the order we always followed for double and triple integrals, right? Dependent, then somewhat dependent, but still independent, half and half, and then independent, right? Okay, let's go for it. So 2 squared 4 plus 1, 5 plus 1, 6, the same square root of 6, right? From the other way. Oh, but be careful. Do you see the catch here? So our integral right here is supposed to depend on it with respect z and y. Look at the variables of the density function. We need to get rid of one of them, right? Which one? X, right? So use this x in terms of x, y, in terms of y and z, to replace our double integrals with respect z and y, to have an integrand with respect z and y as well, right? Okay, what is this? So x, which is 6 minus 2y minus z times y dz dy evaluate it between, what's that, lower limit, 0 and negative 2y plus 6, and 0 and 3. All right? In fact, this integral looks a little harder to evaluate, well, a little longer to evaluate, and on top of that, it had that little catch that we needed to get rid of one of those variables that were not part of the differentials. So, in a way, it wasn't worth the change of the projection, but still, we have to do one of these exercises so you can see how it works to change the projection. So there's a lot that we could have done in chapter 17. There should have been another section, say maybe 16 point, what was that, 9, I think, in which we work with really hard looking solids or regions of integration, but then running with the purpose of running into the situation that we can evaluate or even set up the integrals by projecting onto the xy to force us to work on other projections, the yz or the xz. But it's only a 4-unit class. I wish this class were a 5-unit class to do a bunch of pretty cool stuff. But anyway, maybe in the future, I don't know. All right. Okay, and the result for this integral. Yeah, we were in evaluating, right? You'd better get the same result, right? Okay. So that's another one, okay? Oh, the next one. So now we're going to go directly to the context. A, find the mass of a thin funnel in the shape of a cone. That cone where z varies between 1 and 4. If its density function is 10 minus z. Okay, cone, circular. I think you guys can anticipate what are we going to do as far as the integration, right? What do you think we're going to do later? Project to, and then what do we do? What are we going to do? Polar, right? So, yeah, the minute you see these circular shapes, for sure there's going to be a polar or a cylindrical, depending if it's a triple or a double or a triple integral. Okay, let me try my best to draw this cone. Well, actually, you'll see. So, this cone, it's not actually it doesn't touch the origin because it's a cone that it's bounded below by a plane z equals to 1 and by the plane z equals to 4. So it will be a cone that looks like this. Yeah, actually, they're telling us it's a funnel, right? Not a cone. So, yeah. It's going to look like this, right? So that is, let me shade. This is z equals to 1 and z equals to 4. All right? Okay. All right, what do you guys say we will look at the projection onto the xy plane? All right? So, isn't that going to look like this? Yep. Do you guys agree with this? I mean, if you look at this funnel from the top, you're going to see that that projection. Well, what are the radii? What are the radii of this? Well, actually, you know what, guys? We need to show this algebraically. It might be pretty obvious, but in some cases, it's not obvious. It could be a trap. To stay away from the trap, do the algebra. What kind of algebra? Okay, set this radical equal to 1 and set this radical equal to 4, just to ensure that what you're anticipating to be the limits of the integration is fine, okay? Okay, so the square root of x squared plus y squared equals to 1, and square root of x squared plus y squared equals to 4. Square both sides, what is that going to give us? X squared plus y squared equals to 1, and x squared plus y squared equals to 16. Well, I mean, yes, right? We were right with our anticipation. Unit circle and circle of radius 4, right? So that's 1 and that's 4. Good. Okay. Oh, we haven't written a yes.
Did you also just do it as z equals r, the square root of x squared plus y squared, and then like 1 equals r, and then
Yep. And well, that would be like a simpler way to do it, but that's when we look at this region with the eyes of the polar transformation, right? But it's the same thing. It's the same. Yep. So okay. So we haven't written a domain of integration in a while, you know. So that's x, y, all the points x, y that are. How do we write this domain? X squared plus y squared, 1 and 16. All right. Careful not to write it between 1 and 4 because that's the equation of the circle that has a radius for, all right? Essentially, okay, another way to get this. Oh, look at this. How about square the three sides of the compound inequality? That is 1 less than or equal z squared less than or equal 16. But what is z squared? Isn't that x squared plus y squared less than or equal 16 and greater than or equal to 1? That's another way to get these regions of integration, right? By manipulating the inequality. There's many ways to go about this. I mean, you choose your favorite one. All right, I think we're ready to set up the double integral. Did I? Oh yes, this one we will evaluate. You're gonna like this one, I think. All right. Okay, so number one, yes, z, the partial derivatives, right? So z equals to x squared plus y squared raised to the 1/2. Agree? Yes, we will have to use a chain rule to get the partial derivatives of this equation, of this function, right? Okay. So z with respect x, 1/2 x squared plus y squared to the negative 1/2 times by chain rule multiply by 2x, okay? Divide out the 2's, okay? Divide out the 2's, and well, that negative radical, send it to the denominator with positive exponent, right? And then turn it into a radical in the denominator. Okay, so well, I'm gonna do 1. Okay, so divide out, that's x over x squared plus y squared to the 1/2, and then x over x squared plus y squared, under the radical. All right. In a similar way, with respect y, just change x's with y's. I mean, that's the square root of x squared plus y squared, the denominator of y. All right. Let's set up this integral. Interesting. All right. So, well, they're asking us to find the mass of this funnel. That is m equals the double integral of rho of x, y, z. That's the density function. The big S, where this is over the region R, that projected onto the xy plane. That little donut there. All right. Okay. So let's substitute. Yes. That's 10 minus z times the square root of the squares of the partial derivatives. That is x over square root of x squared plus y squared plus y over the square root of x squared plus y squared plus 1. And for now, let me go about dA. Huge integral, finally, right? One of those we like, right? But actually, don't worry. This one is going to simplify really, really nicely. So, okay, let's see. So that equals, one more thing, guys. This dA can be what? What are the choices? What are going to be the choices for dA? There's 2 of them. Or look at the function in the integrand. Let's get rid of that z in terms of X and Y. How? Oh, look at this. To make the integral look even nicer, right? Yes. All right. So over the region R, that's the double integral over the region R. What's that? Okay, so that is 10 minus root of x squared plus y squared times the square root, okay, x squared over radical squared x squared plus y squared plus y squared radical squared over, that is, x squared plus y squared plus 1 dA. The best news here is the denominator of the first two terms is the same, so we can combine them together, right? Okay, so that equals the integral, the double integral over the region R of 10 minus the square root of x squared plus y squared. Okay, this is times the square root. Okay, combine fractions together, keep the common denominator x squared plus y squared, and perform the indicated operation between the numerators. What is that? X squared plus y squared. Look at this beauty. X squared plus y squared divided by itself. What is that equal to? Plus the other one, square root of 2. You see how this one simplifies really nicely? Okay, dA. So this is all this madness equals to 1 plus 1. That's 2. That's the square root of 2. I'm going to write that square root of 2 outside of the double integral of the region R. Okay, what's that? 10 minus the square root of x squared plus y squared. Let me keep this dA. Okay, so this is as far as we can do, as far as we can go about simplifying our integral. Okay, here is where we look at this integral and go about the method of integration. Do you want to integrate that humongous radical with radical limits? Come on. Circular regions, what do you think we should do? Polar, okay? Polar coordinates. Okay, so that equals to square root of 2, the integral, the double integral of 10 minus, what's that? Again, let me go one step back. This is r squared. But what is the square root of r squared? R, just r, right? What is the A in the world of polar? R dr d theta. R dr d theta. Now help me with the limits. Help me with the limits. 1 to 4. 0 and 2 pi. Come on. This is a baby polynomial to integrate, unlike the previous one, right? You don't want to do the monster from the previous. I mean, you can attempt it. That's fine. All right? Okay. I'm just going to give you the result. 108 pi square root of 2. You can play easy mode or legendary mode. It's your choice, right? It's your choice. What is that? Dark Souls versus Kirby, or yeah? I mean, Elden Ring versus Kirby, right? Yes. All right, let's see. Flux integrals and orientation of a surface. Oh, okay. There's something new. Here's something new, right? Remember how we described these vector valued functions? These vector valued functions describe the trajectory of a particle. I mean, that particle can be anything: a car, an airplane, a rocket, or for real, a particle, an electron, a proton, you name it. There's many particles out there. But the thing here is, those vector valued functions have a sense of direction, right? Either they go from this direction or backwards. What about surfaces? Surfaces can also be oriented, right? But how? They're oriented by their normal vectors. Now, there's two kinds of surfaces. Closed surfaces, think of the different closed surfaces. Well, the sphere. How about the sphere is one of those closed surfaces? What about an ellipsoid? Isn't that another closed surface? But any other surface like a polynomial in x and y with an exponential, those are not closed surfaces. So that's represented by the second picture here. All right? Okay, now here's the thing. For surfaces that are closed, the normal vectors will always point out. That is, they're oriented outside. However, for surfaces that are not oriented, we need to be specific about the orientation. Are we coming in or are we coming out of the surface? But why do we want to do this? Because we're going to learn about a new integral called a flux integral, which is an integral that involves a surface integral. But what is it anyway? Okay, think of a screen. Think of this surface as a screen. So this integral will give us a rate of change of the amount of a fluid going across that surface. You know, like when you open, the easiest case, when you open the window at home in your room, the air coming into the room, right? So because especially these hot days, right? You open your window to get some fresh air, right? Or maybe out, I don't know, maybe you want to get the hot air outside of your place, right? Or, well, in a more engineering point of view, how about those membranes they use to clean wastewater, to get rid of all these waste, of all these ions, and they do a bunch of pretty cool stuff so we can use clean water at home, right? So, well, it turns out that those membranes are surfaces, and, well, there's a flux integral describing the flux, you know, of that fluid going across the surface. So we're going to learn about those integrals. All right? What time it is? Okay. I don't know if we're going to have. Anyway, we'll try our best. So again, okay, what's the idea behind? Because orienting a surface, describing the orientation of a surface involves normal vectors, right? Vectors that are going to point out of the surface or inside the surface in the case of the not closed surface. So here is the thing. We're going to have the following function of x and y, and it's as an explicit function of z, function z. Remember when we created these implicit functions in chapter 15 to take these partials and use these chain rules and all that? Okay, we're going to define this big G function, which is, so what I'm going to do is z minus g of x, y, all right? G of x, y, this is equal to 0, right? And this expression right here is going to be our big G, right? Which is, yeah, we have it here, right? How do we get the unit normal vector in the direction of the gradient? Well, it's just take the gradient and divide it by its magnitude. Didn't we do that at the end of chapter, what was that, 15? When we discussed everything about partial derivatives. Well, let's find the gradient of this function. Okay, the gradients, again, are the partial derivative of the function with respect x. Well, that's going to be negative g of x, the partial with respect y, negative g with respect y, and the partial with respect z. What's the partial with respect z? Isn't that just one? That's this one right here. Okay, divide that by the magnitude of that vector to get the unit vector. Okay, so that'll be, okay, divide by the square root of the components of that vector we just obtained squared, right? I mean, pretty much day one material, but with this new sentence, right? Okay, now let's put this together. Let's derive this flux integral from that idea of orienting a surface versus putting together these what's it called? The surface integrals and all that. Okay, I think you guys are gonna need to flip your page for the derivation. Okay, so let me justify this. I mean, I could give you the formula, work with it, but let's put this together. Okay, I'll try not to take too long with the derivation so we have time to work through the example. Okay, so the double integral of f dotted with big N, remember, what was that? Green's theorem, when we did the second version of Green's theorem, that's the projection of the force in the direction of the normal vectors. That's what we're doing. We're finding the flux, but in space, right? In space. Okay, so what is F? That's the double integral of a vector field M, N, P, whatever that is, times N. Okay, what's N? Isn't that negative G with respect X and negative G with respect Y? 1 divided by its magnitude. What is the magnitude of that? Oh, I'm going to need more space. Negative G with respect X squared plus, well, G plus G with respect to Y squared plus 1. Okay, let me move all this over here. What is the S? Remember how we got ds from that tiny tissue piece of plane? That's the square root of g sub x with g with respect x squared plus g with respect y squared plus 1 dA. Oh, look at this. You will no longer have to evaluate these radicals for a flux integral. Good news. Right? They go away. Sorry. So in the end, all you need is the double integral of the vector field. Because, okay, do you guys agree that in order to have a fluid going across a membrane, there's a driving force needed? It's not going to happen by itself, right? What do we need for that? That vector field, right? That vector field. Negative G with respect X and negative G with respect Y. 1. Do the dot product between these two vectors. Come on, you guys can do dot products, right? So negative F G with respect X minus no, this is supposed to be M, not F. M and plus P dA. Isn't that the same integral we just got in the definition box in the previous page? Yep, that's how we got. All we're doing is substituting the unit normal vector, which is the gradient divided by its magnitude. What else? And then just computing the remaining dot product. That's all we do. That's all it is. Okay, let's do one example. Hopefully we get the chance to complete it. If not, give me a couple minutes today. So, yeah, you guys didn't have to do that last time, but at least today. Okay, find the flux, by this driving force, of course, over the closed surface S equals to 16 minus x squared minus y squared. That is the upside down parabola, which is bounded below by the xy plane. That is a closed surface, right? That means we don't need to any additional conditions about the orientation, because what is the orientation for a closed surface? Always outside of the surface, right? Okay, let's go about it. Let's do a really quick picture here. Okay, so the projection, of course, will be that of a circle. Okay, and that's going to be our upside down paraboloid, right? So that means this is the floor, all right? And what are we going to have? Check this out. We're going to have a fluid going across the paraboloid. It's going to go across the paraboloid. All right, across the paraboloid, and we will have some flux across the bottom, across the what's it called? Across the circular bottom. Okay, so that means we need to set up two flux integrals. Okay, what about them? Number one. So across the paraboloid. So flux which is the double integral over the surface S of F dotted with big N ds, but of course we're not going to get normal vectors. Actually, those got canceled, remember? So we will evaluate So remember this dot product here. So this is M, this is N, and this is P. Alright, just be careful because this partial of Z with respect X, partial of Z with respect Y doesn't have anything to do with the Z from the driving force. Okay, so yeah, so just make sure not to put those together. So what else do we need? We need partial derivatives, right? We need the partial derivative with respect X, that is negative 2X. The partial derivative with respect to Y, that is negative 2Y. And well, let's set up the integral. That is, what's that? That is, okay, x plus y, comma, y, comma, z. How do we get the second vector? Okay, that is, be careful here because this is negative, the partial of the surface with respect x. But didn't we get a negative partial? Right? This negative from the integrand times the negative from the partial derivative becomes positive. Same for the y component. And z is always going to be 1. dA. Let me do at least the dot product. So the dot product will be the double integral over the region. No, I'm not going to integrate over the surface S. xy times 2x. That's going to be, oh, no more vector. 2x times xy, x plus y. Not xy, x plus y plus y times 2y. And lastly, z times 1, which is z. dA. I'm not iterating yet. Alright, so that is equal to, okay, that's the double integral over the surface S. What is that? 2x plus y, 2xy. No, I need space. That equals, that's plus 2y squared plus z dA. Again, this reduces to double integral where dA is dx dy or dy dx. Do you see that z over there? We need to get rid of that z because our integrand cannot have variables other than x and y. So how are we going to do that? Oh, we're given a z, replace it here. 2x squared, which one? Oh, yeah, I see it right here, 2x squared, right? So that is the double integral 2x squared plus 2xy plus 2y squared plus, come on, I'm needing a lot of space. Oh, wait. Plus z, which is 16 minus x squared minus y squared. And what is that? dA. You know what? Let's stop here.